The planet has been rupturing in 3 places at once in the past few days, and not one of those places knows the others exist. A subduction zone north of New Zealand, the middle of the Atlantic Ocean, western Nevada. 3 completely different tectonic systems. 3 completely different mechanical processes. One 36-hour window. Now we could say this is all coincidence, and statistically it might be. But here's what's keeping seismologists up at night. The background rate underneath all 3 of these events had been climbing for weeks before any of them happened. Tonight I'm going to walk you through exactly what this means, why the pattern looks more connected than it actually is, and why the thing buried underneath all 3 of these events is the part that deserves your full attention. Stay with me. Before we begin, if you genuinely enjoy what we do here at Project Nightwatch, hit like and subscribe so you do not miss a single update as the story develops. Drop a comment with where you're tuning in from and tell me this. 3 mechanically opposite tectonic systems activated simultaneously on opposite sides of the planet in 36 hours during an already elevated seismic baseline. So is that a coincidence, or a pattern we do not yet have the language for? Let me know in the comments. Now let us get into it. Part 1. The 36-hour shadow. 3 separate wounds opened in the Earth's crust within 36 hours of each other, and none of them knew the others existed. That's the thing that keeps pulling at the back of your mind when you first look at the data. Not the individual events, those happen. Earthquakes are not news. What becomes news, what becomes something closer to a question you can't quite stop asking, is the arrangement, the geometry, the way these 3 separate systems, operating under completely different mechanical rules, on completely different tectonic regimes, on literally opposite sides of the planet, all chose the same narrow window of time to become visible at once. Let me give you the raw facts first, because the facts matter before the interpretation does, and this is a story where interpretation is going to do a lot of the heavy lifting. Within a window running approximately 36 hours in coordinated universal time, the following happened. A magnitude 6.0 earthquake struck the Kermadec subduction zone, located north of New Zealand in the southwestern Pacific. That's a compressional system, one plate driving under another, the oceanic floor being consumed by the mantle below, stress accumulating across a locked fault interface, and then releasing in a single rupture. Classic subduction behaviour. Then, on the geologically opposite side of the world, 3 separate magnitude 5+ earthquakes strung themselves along the mid-Atlantic ridge within roughly 16 hours of each other. That's a divergent boundary system. 2 plates pulling apart, magma welling up through the fracture, the ocean floor spreading outward over geologic time. Extension, not compression. The polar mechanical opposite of what happened at Kermadec. And then, simultaneously with both of those, the Walker Lane belt of western Nevada continued producing what had grown into a swarm of 218 individual ruptures, ranging from magnitude 1.5 to magnitude 8.0 in depth, and still with no dominant main shock to organise the sequence around. Pause on that for a second. 1 convergent boundary, 1 divergent boundary, 1 continental strike-slip deformation zone, all 3 active, all 3 shallow, all 3 occurring inside a planet that had already been running an elevated seismic baseline for weeks before any of this happened. The depth numbers deserve attention right away because they're going to show up again and again in the data, and they carry an asterisk. Most of these events are being reported at approximately 10 kilometers depth. That number, 10 kilometers, is the United States Geological Survey's default reporting depth for earthquakes, where the depth has not been precisely constrained. It's a procedural placeholder, not a measurement. When you see that number repeat across 3 different tectonic environments, on 3 different sides of the planet, you're not seeing a meaningful geological alignment. You're seeing the fingerprint of how catalogues are built. The Earth didn't choose to rupture at exactly 10 kilometers in Nevada, and at exactly 10 kilometers in the South Atlantic, and at exactly 10 kilometers near New Zealand. The computer assigned that number as a default while better data was still being processed. That matters for how we read the pattern, and we'll come back to it. But here's what the depth artifact doesn't explain away. It doesn't explain the timing. It doesn't explain the tectonic diversity. It doesn't explain why 3 fundamentally different mechanical systems, one compressing, one extending, one shearing, all became visible in the same 36-hour window on a planet already running hot. What you've essentially drawn, if you plot these three events on a globe and connect them, is something that looks uncomfortably like a triangle. Kermadec in the southwestern Pacific, the Mid-Atlantic Ridge cluster running through the central Atlantic, Walker Lane in the American West. These 3 points don't just occupy different regions, they occupy different hemispheres, different ocean basins, different continents, different tectonic categories. The spatial separation is almost theatrical. It's as if the planet chose 3 locations specifically designed to look as globally distributed as possible. And that theatrical quality, that visual symmetry, is the first thing you need to be suspicious of, because the human brain did not evolve to be neutral about patterns. It evolved to find them fast, to find them even when they aren't there. The central question running through all of this is one that seismology doesn't have a clean answer to. Is this 36-hour window of activity meaningful global stress behaviour? Or is it a high-visibility coincidence inside a naturally noisy Earth that we're simply not used to seeing framed this clearly? Hold that question. Because we're going to spend the rest of this trying to answer it, and I'll warn you now that the answer is going to be uncomfortable. The global triangle of rupture geometry sounds like something a thriller writer invented, and in a sense they did, except the thriller writer in this case is the human visual cortex, which is extraordinarily good at connecting dots across space and time into shapes that feel meaningful. When you look at a globe and you see 3 active seismic systems forming a near equilateral triangle spanning the Pacific, Atlantic and American West, something in your pattern recognition machinery fires. It says, that can't be random. The mathematical reality is considerably less dramatic. The Earth has thousands of kilometers of active fault boundaries. The Ring of Fire alone represents over 40,000 kilometers of continuous seismic hazard. Given the frequency at which earthquakes occur globally, and we'll get precise about that frequency shortly, the question isn't whether 3 systems can be simultaneously active. They almost always are. The question is whether 3 specific systems, in 3 specific mechanically distinct regimes, crossing 2 hemispheres, represent something beyond the baseline expectation. And that's where it starts to get genuinely interesting, because the honest answer is, we don't entirely know what the baseline expectation is. The standard figure you'll see cited is somewhere between 70 and 80 magnitude 4.5 and greater earthquakes per week globally. That's roughly 10 per day. When you're generating events at that frequency, clustering becomes not just possible, but mathematically inevitable. If you took those events and distributed them completely at random across time, a Poisson process, the standard statistical model for rare independent events, you would still expect to see multiple systems appearing active within the same 24 to 48 hour window a significant portion of the time. Pure chance produces apparent clusters. This is one of the most counterintuitive facts in probability theory, and it's one that the human brain is spectacularly bad at internalizing. We look at a cluster and we think, that required a cause. But the mathematics says, clusters are what randomness produces. Here's a simple way to feel that. Imagine you have 10 earthquakes per day distributed randomly across the globe. Over a month you have 300 events. Now ask yourself, what are the odds that at least 2 of those events fall within a 12-hour window? The odds are not small. In fact, gaps between events would be far more surprising than overlaps. The clustering isn't the anomaly. The clustering is the expectation. What changes the calculation is when the frequency goes up, when the background rate itself elevates, because then clusters become both more frequent and more visually pronounced. And the background rate, in the weeks leading up to this 36-hour window, had been doing something that requires explaining. The Ring of Fire had been running above its own recent baseline for multiple weeks before this cluster formed. Japan was active, Vanuatu was active, the Peru-Chile subduction system was active. The Tonga-Kermadec system had already produced a magnitude 7.5 in March, with swarm activity continuing through the 22nd, 23rd and 24th of that month in the 6.2 to 7.5 range. The planet wasn't quiet before the 36-hour window, it was already elevated, which means the cluster we're looking at didn't form inside a calm background. It formed inside a system already running warm. That distinction matters enormously for how we interpret what happened. If this cluster appeared against a quiet global background, the anomaly signal would be stronger. If it appeared during an already elevated period, it becomes much harder to separate signal from background, because the background itself may have become the signal. And that's the uncomfortable implication sitting underneath all of this. The question isn't just whether three systems synchronized. The question is whether the elevation underneath all three of them is a fluctuation or a trend. We don't have that answer yet. And if you find that unsatisfying, good, it should be. Because here's the thing about the geometry that nobody says out loud in the standard earthquake coverage. The opposite sides of the planet framing is doing more psychological work than it is doing scientific work. When journalists and commentators describe the Kermadec and mid-Atlantic events as happening on opposite sides of the planet, they are technically correct in a geographic sense, but the planet doesn't have sides. It has a continuous lithospheric shell, broken into plates, with fault systems distributed across its entire surface. There is no geologically meaningful sense in which opposite sides constitutes a special condition. The plates don't know which hemisphere they're in. The stress doesn't orient itself relative to the equator. What's happening when we use that framing is a form of narrative amplification. Hemispheric opposition is psychologically compelling because we're used to thinking about opposites as contrasting or counterbalancing things. Left and right, up and down, north and south. When we say earthquakes are happening on opposite sides of the planet simultaneously, our brains hear something like a system in balance being disturbed at both ends. That is not what's happening geologically. What's happening geologically is that two unrelated fault systems, which happen to be geographically distant because the planet is large, both produce seismicity during the same 36-hour window. The opposition is a function of the planet's size, not a function of any mechanical relationship between the systems. But that cognitive hook is real, and it's one of the main reasons this event pattern feels more alarming than the raw data probably warrants. We're going to try to stay honest about where the alarm is justified and where it's being generated by the architecture of our own perception. And the honest answer is that some of both is happening here. The pattern that appeared during that 36-hour window is simultaneously less coordinated than it looks and more interesting than it should be. Less coordinated because the visual geometry of the triangle is a projection of three randomly placed active systems onto a globe-shaped screen where the human eye will find triangles. More interesting because those three systems happen to represent the full tectonic diversity of the planet: compression, extension, shear, and because they appeared during an already elevated background period, and because one of them, the Walker Lane swarm, was still actively evolving while the other two were already in the record books. That last point is the open edge of the story. Most seismic events, by the time you're analysing them, are complete. The rupture happened, the energy released, the aftershock sequence is decaying, the system is moving back toward a lower energy state. Walker Lane, during the window we're discussing, was not doing that. It was still generating new ruptures, still adding events to a swarm that had already exceeded 200 individual earthquakes, still refusing to organise itself around a main shock, still behaving, in other words, like a system that hadn't decided what it was going to do yet. And that unresolved quality, that sense of an open process still running, is what separates Walker Lane from the other two systems in this cluster, and what makes it the most important thread to pull on as we go deeper. Because the Kermadec earthquake happened, it's done. The mid-Atlantic sequence happened, it's in the catalogue. Walker Lane was still happening, which means it was still uncertain, which means it was still dangerous in a way that past tense events simply aren't. But before we get to the uncertainty at the edge, we have to understand the mechanism at the centre. And the mechanism at the centre starts in the Pacific, where a subduction system had been accumulating stress for months before it announced itself to the world in the most unambiguous terms possible. Part 2. The Pacific Trigger Zone. The Tonga-Kermadec subduction system is one of the most seismically prolific strips of real estate on the planet, and that's a competitive category. To appreciate what competitive means in this context, consider what it's competing against. The Cascadia subduction zone off the Pacific northwest coast of North America, the Chile-Peru Trench, which produced the largest earthquake ever instrumentally recorded, the Japan Trench, which generated the 2011 Tohoku disaster, the Sunda megathrust, which produced the 2004 Indian Ocean earthquake and tsunami. These are the canonical examples of seismic hazard at the planetary scale, the systems that appear in textbooks and disaster preparedness documents and government risk assessments. Tonga-Kermadec belongs in that company. It earns its place not through a single defining catastrophe that fixed it in public memory, but through the sheer sustained volume of seismic energy it releases year after year, decade after decade, as one of the fastest converging and most continuously active subduction systems on Earth. It runs roughly from the Tonga Islands southward through the Kermadec Islands toward the northeastern tip of New Zealand's North Island, where it transitions into the Hikurangi subduction zone. From end to end, you're looking at something in the neighbourhood of 2,500 kilometres of active subduction interface, 2,500 kilometres where the Pacific Plate is being driven at roughly 6 to 7 centimetres per year beneath the Australian and Tonga plates. That convergence rate matters. It's one of the higher rates of plate convergence on Earth, and convergence rate is one of the primary drivers of stress accumulation on a subduction interface. The faster the plates converge, the faster stress builds on the locked portions of the interface, and the shorter, in statistical terms, the average recurrence interval between major earthquakes. That interface is not a smooth surface. This is worth emphasizing because the word interface suggests something planar and regular, like two sheets of paper pressed together, and the reality is almost the opposite. It's a complex, segmented, geometrically variable contact zone with sections that lock, accumulate stress, and eventually fail in earthquakes, and other sections that slide more continuously, releasing stress in smaller increments without building toward major ruptures. The difference between a locked segment and a creeping segment is not always visible at the surface. It requires geodetic measurements, GPS networks, satellite radar interferometry to map the spatial pattern of coupling across the interface. Where coupling is high, stress builds. Where coupling is low, it bleeds off. The Tonga Kermadec system has both, and the geometry of where the high coupling zones are located relative to each other shapes the statistical geography of where future large earthquakes are most likely to occur. Understanding why Kermadec matters in this 36-hour story requires going back to March, because the March events were the stress redistribution that set the table for everything that followed. This is a point that gets lost in coverage that treats the April 17th magnitude 6.0 as an isolated event. It wasn't isolated. It was the latest expression of a process that had been running for weeks, the most recent exhale in a breathing cycle that began with a much larger intake of mechanical breath in early spring. In March, the Tonga segment of this system produced a magnitude 7.5 earthquake. That is not a small event, and the energy comparison is worth making explicit because magnitude scales are logarithmic in ways that human intuition doesn't naturally track. A magnitude 7.5 releases roughly 32 times more energy than a magnitude 6.5, and over 1,000 times more energy than a magnitude 5.5. Put it in more concrete terms, the difference between a magnitude 5 event and a magnitude 7.5 is roughly the difference between something that rattles dishes and something that collapses bridges. The March main shock was a significant mechanical event in a system that has produced significant mechanical events before, and it didn't just release energy, it redistributed it. When a fault segment ruptures at magnitude 7.5, the surrounding rock doesn't just shrug and return to baseline, it adjusts. The stress that was concentrated at the rupture point distributes outward to adjacent fault segments, to parallel structures, to connecting zones in the broader system. This process has a name: static stress transfer. The rock that was loading the fault that just broke now has a different stress state, and that changed stress state gets transmitted at the speed of elastic wave propagation to the rock immediately surrounding the rupture zone. Some adjacent areas experience increased stress. They've been loaded by the redistribution, pushed closer to their own failure thresholds. Other areas experience decreased stress. They've been unloaded, relieved of some of the stress that was building toward their own rupture. The pattern of stress increase and decrease around a fault rupture is not random. It follows from the geometry of the rupture and the mechanical properties of the surrounding crust, and it can be modelled with reasonable accuracy using what seismologists call Coulomb stress change calculations. Think of it like squeezing a tube of toothpaste in the middle. You relieve the pressure at the squeeze point, but you increase it at both ends. The toothpaste doesn't know which end it's going to come out of. The fault system doesn't always know which adjacent segment is going to fail next, but something is going to get loaded, and the question is always when. In the case of the Tonga Kermadec system, the geometry of the March rupture determined which adjacent segments received increased loading, and the timing of subsequent events in the system is at least partially a function of how close those loaded segments were to their pre-existing failure thresholds when the additional stress arrived. The swarm activity that ran from March 22nd through March 24th, with events ranging from magnitude 6.2 to the upper 6 range, was the system's initial response to that stress redistribution. These weren't random earthquakes. They were the Kermadec Tonga system rebalancing, adjacent segments responding to the stress changes introduced by the March main shock, failing at accelerated rates because their local failure thresholds had been effectively lowered by the stress loading they received from the primary rupture. The spatial distribution of those swarm events, where they occurred relative to the March main shock rupture zone, would be expected to correlate with the regions of maximum Coulomb stress increase. This is standard seismological behaviour. It fits the model. The system was doing what well-studied subduction systems do after a major rupture, and then something happened that often happens in active subduction systems, particularly at high coupling, fast converging interfaces. The seismicity didn't cleanly decay. Instead of following the standard modified Omori decay curve, where aftershock frequency drops predictably with time at a rate that can be mathematically described by a power law, the system maintained an elevated level of activity into April, still generating magnitude 5 and 6 events, still displaying what seismologists would describe as heightened coupling behaviour, the fault interface behaving as though it hasn't yet found its post-main shock equilibrium. This deviation from the standard decay model isn't anomalous in any alarming sense. It's a recognised feature of subduction zone behaviour, particularly in systems with complex fault geometry and heterogeneous coupling distributions. When the rupture zone is geometrically complicated, or when the stress redistribution affects multiple segments with different mechanical properties, the post-main shock decay can be prolonged, irregular, or punctuated by secondary activations that briefly elevate the seismicity rate above what the modified Omori curve would predict. The April 10th through April 17th continuation of elevated seismic release, the window that contains our magnitude 6.0 Kermadec event, is consistent with this interpretation. This isn't a random new earthquake occurring against a quiet background. It's the continuation of a process that began in March, a multi-week activation cycle in a system that was already primed by a major stress redistribution event. The April 6.0 isn't a new story. It's the most recent sentence in a paragraph that started being written 7 weeks earlier. Subduction zones behave as interconnected stress ribbons. That phrase sounds metaphorical, but it's actually a reasonable mechanical description of what the fault interface is and how it functions. The interface isn't a single plane. It's a collection of interlocking segments, some locked, some creeping, some in intermediate states, that communicate stress to each other through the elastic properties of the surrounding rock. When one segment fails, the stress it carried doesn't vanish. It moves. It propagates along the ribbon, loading the next segment, increasing the probability of failure there, setting up the conditions for the next event. The ribbon isn't infinite in length. There are structural discontinuities in subduction zones where stress transfer becomes less efficient, but along a continuous, geometrically coherent section of interface, the stress communication is real and measurable. The concept of segment reactivation waves is useful here. Not an official term, more of a conceptual tool, but it describes the way that seismic activity can appear to move along a subduction zone over days or weeks following a major rupture. You can find historical examples of this in the geological record and in the instrumental record. The 2011 Tohoku earthquake in Japan was preceded by weeks of elevated seismicity in adjacent segments of the Japan Trench system, a foreshock sequence that, in retrospect, was consistent with stress transfer propagating toward the eventual rupture zone. The 2004 Sumatra Andaman earthquake was followed by a months-long activation sequence that progressively lit up adjacent subduction segments to the north and south, the Nias earthquake in March 2005, the Mentawai region activity that followed, all consistent with stress redistribution cascading along the Sunda megathrust system over an extended period. These are not coincidences, and they are not cases of one earthquake causing another in a simple billiard ball chain reaction sense. They are examples of stress redistribution cascades, systems responding segment by segment to the changed stress environment created by a major rupture on timescales that can extend from days to months depending on the geometry and mechanical properties of the interface. The Kermadec magnitude 6.0 on April 17th, read in this context, is not a standalone event. It's a mid-cycle release point in a system that has been actively redistributing stress since March. Not the peak event, the March 7.5 was that. Not the beginning of a new sequence, the March swarm was that. Something more like a continued exhalation from a system that took a deep breath in March and still hasn't fully exhaled. The lungs aren't empty yet. The pressure hasn't equalized. The April 6 is one breath in a longer respiratory cycle, whose duration and eventual endpoint the system will determine on its own schedule. Now here's where this becomes critical for the central question we've been tracking. If the Kermadec event is a predictable continuation of post-main shock stress redistribution in the Tonga-Kermadec system, and the evidence is consistent with exactly that interpretation, then that's a complete and mechanically satisfying explanation for the Pacific component of this cluster. It fits known physics, it fits the historical analogues, it fits the timeline, it fits the spatial pattern of activity within the system. The Pacific side of the story has a coherent local narrative with well-validated mechanisms underneath it. Pacific side explained. But the Pacific explanation explains the Pacific. It does not explain the Atlantic, and it does not explain Nevada. To connect those systems, to build a mechanical bridge from a subduction zone in the southwestern Pacific to a divergent boundary in the central Atlantic, to a continental strike-slip deformation belt in the American West, you need a different class of mechanism. Not local stress redistribution, which has a range measured in hundreds of kilometers, something with global reach. And this is where seismology starts to get genuinely uncomfortable, because the mechanisms that could theoretically create that kind of global reach are real, but their significance is controversial, their attribution is difficult, and their ability to explain this specific pattern is, at best, partial. The first mechanism to consider is dynamic triggering via seismic wave propagation. When a large earthquake occurs, and the March magnitude 7.5 qualifies, it generates seismic waves that travel through the Earth's interior and along its surface. Body waves, P waves and S waves travel through the Earth's interior at speeds of several kilometers per second, arriving at distant locations within minutes of the main shock. Surface waves travel more slowly but carry more energy over long distances, and they can travel completely around the planet within approximately 1 hour. These waves carry energy. When those waves pass through a fault system that is already close to failure, already loaded near its threshold, the transient stress change they introduce, even a very small one, can be enough to push the system over the edge. This is not a theoretical concept. It has been documented empirically in multiple well-studied cases. The 2002 Denali Fault earthquake in Alaska triggered seismicity as far away as Yellowstone, more than 3,000 kilometers distant, within hours of the main shock. The 1992 Landers earthquake in California triggered earthquakes across much of the western United States within hours of the main shock, at distances far beyond what static stress transfer could explain. Dynamic triggering is a real phenomenon with a real physical mechanism and a real observational record. The key phrase in all of those examples is close to failure. Dynamic triggering isn't a universal remote control for seismic systems. It doesn't reach across the planet and activate any fault it touches. It works when the target system is already sitting near its failure threshold, already stressed to the point where only a small additional perturbation is needed to initiate slip. It doesn't load faults from zero. It doesn't create seismic hazard where none existed before. What it does is advance the timing of earthquakes that were already going to happen, potentially by months or years, by providing the marginal increment of stress that pushes a near-critical system over its threshold a little earlier than it would have crossed on its own. This makes attribution almost impossible in individual cases. If the Mid-Atlantic Ridge was already primed for seismicity, and given that it's a continuously active spreading centre, with transform faults that are perpetually cycling through stress accumulation and release, it almost certainly had segments near failure at any given time. Then the passage of surface waves from the March Tonga event could have advanced the timing of those 3 magnitude 5 events. Or those events could have happened anyway, on their own schedule, entirely independent of anything that occurred in the Pacific. Distinguishing between those two scenarios from the data alone is somewhere between very difficult and impossible. You would need to know the pre-event stress state of each specific transform fault that ruptured, which is information that no monitoring system currently provides. Without that information, you cannot determine whether the Tonga waves provided the marginal increment that triggered the events, or whether the events were going to happen on their own timeline regardless. The scientific controversy around how long dynamic triggering can remain meaningful deepens this problem considerably. Most researchers would accept a triggering window of hours to perhaps a few days following the passage of the main shock's seismic waves. The waves arrive, they perturb near critical faults, and any triggered events occur within that short window while the transient stress change is still relevant. Some studies have suggested that more complex processes, perhaps involving fluid redistribution driven by the wave passage, or interaction with slow slip that was already underway, can extend the effective triggering window to weeks or even longer. But the longer you extend the triggering window, the weaker the statistical case becomes. A triggering window of hours is tight enough that coincidental events are unlikely to fall within it. A triggering window of weeks encompasses so many potential random events that the statistical argument for a causal connection dissolves into the background noise of normal seismicity. There's also the concept of static Coulomb stress transfer, which operates through a completely different mechanism and on a completely different timescale than dynamic triggering. Static stress transfer works through the permanent deformation of the crust around a rupture zone, the changed stress state that persists indefinitely after the earthquake waves have died away. Unlike dynamic triggering, which operates through the transient passage of waves, static stress transfer is a permanent feature of the post-main shock stress field. It lasts. It doesn't decay on a timescale of hours or days. It persists until subsequent events redistribute the stress field again. This makes it the most well-validated mechanism for explaining triggered seismicity in the weeks and months following a major earthquake. But its range is severely limited. For most earthquakes, the static stress changes that are large enough to meaningfully affect fault failure probability are confined to distances roughly equal to a few fault lengths, perhaps a few hundred kilometers for a magnitude 7.5. Beyond that range, the static stress changes become too small relative to the ambient stress fluctuations in the crust to have reliable effects on failure timing. The Atlantic and Nevada are not a few hundred kilometers from Tonga. They are thousands. Static stress transfer cannot reach them in any meaningful sense. So you have two mechanisms: dynamic triggering, which has global reach but short duration, and static stress transfer, which has persistent effects but limited range. Neither one cleanly explains a connection between a March main shock in Tonga and events in the Atlantic and Nevada weeks later. Dynamic triggering could explain the global reach, but not the weeks-long delay. Static stress transfer could explain the weeks-long persistence, but not the global range. And there's no well-validated third mechanism that has both properties simultaneously. Which means that if there is a connection between the March Pacific events and the April Atlantic and Nevada activity, it operates through a chain of transfers that is long enough and complex enough that attributing cause and effect becomes statistically indistinguishable from coincidence. This is the uncomfortable takeaway from the Pacific deep dive. The Kermadec event fits the physics perfectly and tells a coherent local story. It's a satisfying chapter in a well-understood narrative of subduction zone stress redistribution following a major rupture. But it cannot, on its own, and cannot through either of the available long-range mechanisms, carry the explanatory burden for the global pattern. The Pacific system is solved, the global system is not, and that gap between local explanation works and global explanation fails is the crack in the floor of this story through which the more unsettling possibilities begin to seep. If you can't explain the global cluster with a single triggering event and a validated physical mechanism, you're left with two remaining options. Either the three systems coincidentally became active in the same window, the statistical clustering explanation, where elevated background rates made temporal overlap probable even without any physical connection, or there is some larger scale condition affecting the global seismic system that current models don't account for. Both of those possibilities are live. Neither one is fully comfortable. And as we move from the Pacific to the Atlantic, the explanation doesn't get cleaner, it gets messier. Part 3. The Mid-Atlantic Ridge Cluster. The Mid-Atlantic Ridge doesn't get the attention it deserves, and there are reasons for that which tell you something important about how we construct earthquake narratives. The construction happens gradually, almost invisibly, through decades of media coverage that selects for certain kinds of events and certain kinds of locations and certain kinds of outcomes. Subduction zones check every box. They produce the largest earthquakes on Earth. They generate tsunamis. They build island arcs and volcanic chains. They sit at the edges of continents, adjacent to coastlines, near cities, near populations whose vulnerability gives the seismic hazard human scale and human consequence. They are, in every relevant sense, the most cinematically appropriate boundary type for disaster scenarios, and the media ecosystem around seismic hazard has spent decades reinforcing the idea that subduction equals danger and everything else equals background. The story of subduction is legible. Plate goes under, stress builds, fault ruptures, ground shakes, wave forms. Beginning, middle, catastrophic end. It fits the narrative architecture that journalism requires. The Mid-Atlantic Ridge sits outside that frame entirely, and it pays a significant epistemic price for doing so. It's a divergent boundary, two plates pulling apart, running roughly north to south through the centre of the Atlantic Ocean, surfacing in Iceland as a visibly active rift zone of geysers and fissures and occasional eruptions, then descending southward through the middle of the ocean to the waters off Antarctica. At its northern end, it connects to the Arctic Ridge System. At various points, it spawns transform faults that cut across the spreading axis at right angles, creating complex zones of shear between offset ridge segments. It is one of the most geologically significant structures on Earth. It's where new oceanic crust is continuously manufactured, where magma wells up from the mantle and solidifies into basalt, where the Atlantic Ocean grows slightly wider every year. The rate of spreading varies along its length, from a few centimetres per year in the north to somewhat faster in the south. But the process is continuous and has been operating without pause for roughly 200 million years. The Atlantic Ocean exists because this ridge exists. The separation of the Americas from Europe and Africa, one of the defining geological events of the past 200 million years, is still in progress, still being driven by the magmatic upwelling that the ridge represents. It is, in the most literal sense possible, where the Earth is making more of itself. That's not a metaphor. New crustal material is being produced at this boundary right now, today, while you're reading this, while seismometers on the ocean floor are logging events too small to appear in any public catalogue. The ridge is not a static feature. It is an active manufacturing process operating at geological speed, and the earthquakes it generates are part of the mechanical expression of that process. And seismically, it's constantly active. Not in the magnitude 7 and 8 range that subduction zones regularly produce. The largest mid-Atlantic ridge earthquakes tend to cap out around magnitude 7, and events that large are genuinely rare along most of the ridge's length, but in the continuous low to moderate range that keeps a steady low-level hum of seismicity running along the entire length of the system. Transform faults, which cut perpendicular to the ridge axis connecting offset spreading segments, generate most of the seismicity. These are strike-slip systems, releasing the stress that accumulates as adjacent ridge segments spread at slightly different rates. The transform fault is essentially a mechanical connector between two spreading centres that aren't perfectly synchronized. It accommodates the differential motion between them. When the accumulated stress on the transform fault exceeds the frictional strength of the fault plane, the fault ruptures in an earthquake, then it reloads, then it ruptures again. This is the engine that runs at moderate magnitude along the full length of the ridge, segment by segment, transform by transform, producing the background seismicity that the ridge contributes to the global catalogue without anyone paying much attention to it. Magnitude 5 events on the Mid-Atlantic Ridge are not news. They happen regularly. Distributed across a ridge that spans tens of thousands of kilometres, any given week will typically produce several such events scattered along its length. If you pulled up the global seismic catalogue for any random week in the past decade and filtered for Mid-Atlantic Ridge events above magnitude 5, you would find them. Not every week, not with the density we saw in this particular window, but often enough that the existence of Mid-Atlantic Ridge seismicity is not by itself a finding worth reporting. The ridge is active. It has always been active. It will be active next week and the week after that. So why does the April cluster matter? Here's the specific thing that changes the calculus. 3 magnitude 5+ events within approximately 16 hours, not distributed along the full length of the ridge the way normal background activity would be, but occurring in geographic proximity across adjacent segments. That compression in time and relative concentration in space is what separates normal background activity from pattern worth noting. The individual events are unremarkable. The temporal packaging is less so. Let me be specific about what geographic proximity across adjacent segments actually means in this context, because the scale involved is easy to misread. When I say the events were geographically proximate, I don't mean they were close in the way that two buildings on the same street are close. Transform faults on the mid-Atlantic ridge can be separated by tens to hundreds of kilometers. 3 events on adjacent transform systems could still span a few hundred kilometers of ridge. That is a large area by human standards. By the standards of the ridge system, which runs for tens of thousands of kilometers from pole to pole, that same few hundred kilometers represents a relatively compact segment, a small fraction of the total ridge length becoming active in a compressed temporal window. The comparison that matters is not the absolute distance between events, it's the ratio of active segment length to total ridge length, and how that ratio changes during the window in question. Consider what's actually happening mechanically at a transform fault on the mid-Atlantic ridge. You have 2 ridge segments, offset from each other by perhaps tens to hundreds of kilometers, connected by a strike-slip fault running perpendicular to the ridge axis. As the plates spread, the 2 segments don't spread perfectly in sync. One might be slightly more active, slightly more productive of new crust than the other. The transform fault accommodates this mismatch. Stress accumulates along the fault at a rate determined by the differential spreading velocity between the 2 segments it connects. Periodically it fails in an earthquake. After the earthquake, the stress on that fault section drops, the system reloads, and the cycle begins again. This process is essentially continuous and is, in normal circumstances, entirely independent of what's happening at the adjacent transform fault 50 kilometers away. The 2 faults share a tectonic environment and a general stress orientation, but they don't directly communicate stress to each other in the short-term sense. Their failure cycles are determined by their own local loading rates and their own local frictional properties. Under standard conditions, you would not expect them to fail in close temporal succession unless they happen to be near their respective failure thresholds at the same time by coincidence. For 3 of these systems to produce magnitude 5+ events within 16 hours of each other, you need either coincidence, 3 independent systems that happen to be near their failure thresholds, all failing in close temporal succession, or some kind of stress pulse propagating along the ridge axis, triggering a cascade of failures at multiple locations. The first explanation is plausible but requires an uncomfortable amount of coincidence given the short time frame. It requires not just that 2 adjacent transform faults happen to fail close together in time, which would be notable, but that 3 did, which is more notable still. The probability of a specific temporal coincidence decreases as the number of independent systems required to coincide increases. 3 isn't necessarily beyond the range of coincidence, but it's far enough along that curve to make the alternative worth considering. The second explanation, a stress pulse propagating along the ridge, is mechanically possible, but would require a mechanism we don't currently have strong evidence for in this context. What would cause a stress pulse to propagate laterally along a ridge axis? One candidate is dynamic stress from a passing seismic wave generated by a distant large earthquake. If the March Tonga main shock generated surface waves that travelled around the planet and reached the mid-Atlantic ridge, those waves would have exerted transient stress changes on every transform fault they passed. If multiple transform faults along a segment of the ridge were already near their failure thresholds, the passage of the wave could potentially advance the timing of multiple failures. This is dynamic triggering at work, the same mechanism we discussed in the context of the Pacific. But the timing is the problem. Dynamic triggering from surface waves operates on a timescale of minutes to hours after the wave passage. The March main shock was weeks before the April cluster. The waves from that event have long since dissipated. A different triggering event, closer in time to the April window, would be needed to produce wave-driven clustering, and no obvious candidate exists in the catalogue. Another candidate for stress propagation along the ridge is ridge-parallel fluid migration. Hydrothermal systems are active along mid-ocean ridges, and fluid pressure changes can affect fault stability in ways that seismic wave propagation cannot. If a fluid pressure pulse migrated along a permeable zone parallel to the ridge axis, it could potentially perturb the failure thresholds of multiple transform faults in sequence. This mechanism has been invoked to explain certain swarm sequences in volcanic and geothermal environments. It's slower than seismic wave triggering, operating on timescales of hours to days rather than minutes. It's also very difficult to document in the deep ocean, where hydrothermal monitoring is sparse. This isn't an evidence-based explanation for what happened in April. It's a mechanically available possibility in the catalogue of things that could, in principle, produce the observed temporal clustering. The distinction matters. Here's the deeper question underneath the immediate pattern, and it connects directly back to the central thread we've been tracking. Ridge systems are essentially continuous global fracture lines. The Mid-Atlantic Ridge, the East Pacific Rise, the Indian Ocean Ridge System, these are the seams of the planet, the places where the lithospheric shell has been pulled apart to the point of separation. The lithosphere is thinner along ridge axes than anywhere else on the Earth's surface. The thermal gradient is steeper. The rock is younger, less consolidated, more recently emplaced from the mantle below. If there is such a thing as a global stress redistribution, following a major seismic event or series of events, the ridge system, being the mechanically weakest part of the lithosphere, might be the first place that redistribution would become visible. A rigid plate can transmit stress across thousands of kilometers to a plate boundary that is already close to failure. The ridge, as the weakest boundary, might function as something like a global stress relief valve, the place where diffuse distributed stress elevations in the broader system express themselves first, in the form of the small to moderate seismicity that the ridge generates continuously. This is speculative. There's no validated model that treats ridge systems as global stress indicators in the way that statement implies. The idea that the ridge serves as a kind of canary for global stress states is intuitive on mechanical grounds, but hasn't been developed into a testable, quantitative framework that the seismological community has evaluated and either accepted or rejected. It sits in the space of plausible ideas that haven't been properly examined, partly because examining them properly would require a quality of mid-ocean ridge monitoring that doesn't currently exist. And that's the point that needs to be underlined in a way that most discussions of mid-Atlantic ridge seismicity don't bother to underline. The speculation isn't absurd on mechanical grounds, but it points towards something important. We don't have a unified monitoring model for ridge seismicity the way we have for subduction zone seismicity. The ridge systems are instrumentally under-monitored, oceanographically difficult to access, and scientifically deprioritized relative to continental margins. We may simply not have the data infrastructure to know what normal ridge clustering looks like at the level of detail that would allow us to say confidently whether what happened in the Atlantic during this window was unusual. To monitor a subduction zone, you deploy seismometers on land in countries that have national seismic networks, in regions where there is ongoing scientific and governmental interest in earthquake hazard, because people live there and infrastructure exists and there is funding justification. The resulting networks are dense, well calibrated, maintained over decades, and produce catalogues that are both comprehensive and historically deep enough to characterize normal behavior patterns. To monitor the Mid-Atlantic Ridge in comparable detail, you would need a network of ocean bottom seismometers distributed across tens of thousands of kilometers of seafloor, maintained against the corrosive and high-pressure environment of the deep ocean, at costs that current funding structures don't support. The existing ocean bottom seismometer deployments on the Mid-Atlantic Ridge are research instruments, deployed for specific studies over limited time periods, not permanent monitoring infrastructure. The global seismic network does detect Mid-Atlantic Ridge events above a certain magnitude threshold, but the completeness of that catalogue below magnitude 4 or 5 is poor compared to what exists for well-monitored continental regions. Events are missed. Small swarms that would be fully captured on land are partially or entirely invisible in the deep ocean. That uncertainty is not a small caveat. It's a significant gap in the epistemic foundation of the argument. When we say that 3 magnitude 5 events clustered within 16 hours on the Mid-Atlantic Ridge is notable, we're making a comparison to a baseline that we haven't fully characterized. The catalogue exists, but the statistical analysis of transform fault clustering at this temporal and spatial scale hasn't been done in a way that would let us assign a precise probability to this observation. Is 3 magnitude 5 plus events on adjacent ridge segments within 16 hours a 1 in a decade occurrence? A 1 in a year occurrence? Something that happens several times a year but is rarely noticed because nobody is framing it in a global cluster context? We don't know. The catalogue depth and completeness required to answer that question with confidence doesn't exist for the Mid-Atlantic Ridge the way it would for, say, the Japan subduction system or the San Andreas fault zone. This is worth pausing on, because the absence of that baseline doesn't just create uncertainty about the significance of the April cluster. it creates asymmetric uncertainty. We can't say the cluster is anomalous because we don't have a reliable baseline against which to measure anomaly. But we also can't say it's routine because we don't have the catalogue completeness to know what routine looks like at this resolution. The uncertainty cuts in both directions, but it cuts harder against claims of anomaly than against claims of normality, because the default assumption in the absence of evidence is that a system is doing what it usually does. What we're missing is the evidence that would let us confidently challenge that default assumption. And yet, and this matters, the three events are in the catalogue. They happened. Their timing is what it is. They add a data point to the global cluster picture regardless of whether we can precisely quantify their significance. A data point you can't fully interpret is still a data point. In the absence of a mechanism connecting them to the Pacific and to Nevada, they become the most uncertain component of the pattern, the element most consistent with pure coincidence, but also the element where our analytical tools are least adequate to confirm or deny that coincidence. The Atlantic events sit at the intersection of two different epistemic problems: the attribution problem, which we can't solve because the distance between systems is too large for confirmed triggering mechanisms, and the baseline problem, which we can't solve because the catalogue for this specific boundary type at this specific resolution is insufficient. Two different reasons we can't close the question, both real, neither resolvable with what we currently have. What the Atlantic events do, perhaps more than anything else, is remind us that the global seismic system is not composed only of the dramatic, well-monitored subduction systems that get all the press. The ridge systems are out there, continuous and active, largely invisible in the public narrative, running their own thermal and mechanical logic in the middle of the ocean. The Earth is making new crust right now, through a process that generates seismicity as a mechanical byproduct, in a location that most people would struggle to point to on a map, and that almost no media coverage has ever treated as seismically relevant. If the global baseline is truly elevated, and we're going to examine that question directly, the ridge systems will reflect that elevation, whether or not we're watching them carefully. The reflection will be there in the catalogue whether or not anyone is reading the catalogue with the right questions in mind. And the fact that they appeared in this cluster, even in the secondary role, is a data point that deserves more attention than it typically receives. The Mid-Atlantic Ridge isn't just background. It's a globally distributed fracture system that has been operating for 200 million years and will continue operating long after every subduction zone currently receiving scientific attention has been superseded by some future configuration of the plates. Treating it as background noise because it doesn't produce tsunamis is a choice that the field of seismic hazard assessment has made for understandable practical reasons, but it is a choice, and choices about what to monitor and what to deprioritize shape the catalogue that future researchers will use to characterize normal behavior. The Mid-Atlantic Ridge cluster in April is partly invisible because the infrastructure to make it fully visible doesn't exist. That invisibility is itself a scientific problem, separate from the question of whether this specific cluster is significant. The central thread pulls at this point. We have a Pacific system that makes local sense but can't explain the global picture. The Kermadec event fits the stress redistribution story from March. It's a coherent local narrative with well-understood physics, but it doesn't reach the Atlantic. We have an Atlantic system that doesn't fit neatly into any triggering narrative and may simply represent coincidental clustering of background activity, compounded by the fact that we don't have the baseline characterization to know whether it's coincidental or not. The combination of the two doesn't produce clarity. It produces something more like a fog where individual shapes are visible but their relationships remain undefined. The shape of that fog is worth describing because it has a specific character that matters for how we approach what comes next. It's not the fog of total ignorance, where nothing is visible and every explanation is equally possible. Individual features are clear. The Kermadec event is understood. The Mid-Atlantic Ridge operates on known mechanics. The catalogue entries are real. The timestamps are accurate. The individual shapes are visible. What's invisible are the connections between them, the causal threads that would let us say, this happened because of that, in a way that would satisfy a physicist's demand for a validated mechanism. The fog is in the space between the shapes, in the relationships rather than the objects. And that particular kind of fog, clear objects in an unclear relational field, is harder to navigate than simple ignorance would be, because the clarity of the individual objects keeps inviting the inference that the relationships between them should be equally clear. They're not, And moving into Nevada, that fog doesn't lift. It changes character. It becomes less like distance ambiguity, the kind of uncertainty that comes from two systems being separated by thousands of kilometers and therefore beyond the range of any confirmed triggering mechanism, and more like proximity that still somehow refuses to resolve. Walker Lane is in the same tectonic system as the North American plate. It's geographically closer to the Pacific Basin than the Atlantic is, and it's still not explained. Closeness, it turns out, doesn't resolve the fog. It just changes the shape of what you can see through it. Part 4. Walker Lane and the swarm with no centre. 218 earthquakes, and not one of them has stepped up to be the main shock. Sit with that for a second, because it's stranger than it sounds. In the standard model of how seismic sequences work, the model that seismologists have been refining since the late 19th century, earthquakes organise themselves around a dominant event. The main shock happens first, or near the beginning. It's the largest rupture in the sequence. Everything before it, if anything comes before it, is technically a foreshock. Everything after it is an aftershock. The whole sequence has a centre of gravity, a defining moment around which the rest of the activity arranges itself like planets around a star. The main shock is the thing that names the sequence. The 2011 Tohoku earthquake, the 2004 Sumatra earthquake, the 1994 Northridge earthquake. The earthquake gets a name because the earthquake is the event. Walker Lane, during the window we've been examining, refused to give anyone a name. 218 individual ruptures spread across days, spread across space, spread across a population of faults that seismology doesn't have a clean map of, and not one of them large enough, not one of them dominant enough, to stand up and say, this is what this sequence is. The swarm had no centre, it was all periphery. That's the thing about the Walker Lane swarm that keeps pulling at attention, the thing that separates it from the other two components of this cluster, in a way that matters both mechanically and, in the most direct human sense, practically. The Kermadec event happened, and is now a completed entry in the seismic catalogue. Past tense, fixed coordinates, known magnitude. The Mid-Atlantic Ridge cluster happened, and is now historical record. Done. Walker Lane was still happening, still generating new events while we were analysing the other two, still without the organising event that would let seismologists say with any confidence, this is what it was, this is what it became, this is over. That open-ended quality is not just scientifically interesting, it's the thing that makes Walker Lane the most consequential component of the global pattern for the people who actually live near it. And understanding why requires understanding what Walker Lane actually is, because it's one of the more underappreciated tectonic features in the continental United States, hiding in plain sight behind the much more famous fault system to its west. The Walker Lane belt runs through western Nevada and eastern California, in a roughly northwest-southeast orientation, paralleling the Sierra Nevada mountain range on one side and the Basin and Range province on the other. It's not a single fault. It's not even a simple collection of faults. It's a deformation zone, a region where the crust is being pulled, sheared, stretched, and broken across dozens of structures simultaneously, with the accumulated strain distributed across that entire population of faults rather than concentrated on any single plane. Geologists classify it as a transtensional zone, which is a technical way of saying it's experiencing two different kinds of stress at the same time: strike-slip shearing, where crustal blocks slide horizontally past each other, and extension, where the crust is being pulled apart laterally. The combination of those two stress regimes creates a mechanical environment that is geometrically complex in ways that make standard seismic hazard assessment genuinely difficult. Here is the number that should make you take Walker Lane more seriously than most people do. This zone accommodates somewhere between 20 and 25% of the total relative motion between the Pacific Plate and the North American Plate. 1/4. The San Andreas Fault System, the one that has its own disaster movie franchise, the one that every Californian grows up being told is the big one, gets the vast majority of the public attention and the vast majority of the research funding. And it deserves that attention. It's a major, active, potentially catastrophic fault system, but it doesn't do all the work. 1/4 of the plate boundary motion that the San Andreas is supposed to be accommodating is actually being handled by Walker Lane, quietly, across a diffuse zone of distributed faulting that most people outside the geoscience community have never heard of. The The reason this matters mechanically is that a diffuse deformation zone behaves fundamentally differently from a single dominant fault. With a structure like the San Andreas, you have a primary fault plane that accumulates strain over decades, locks progressively as stress builds, and then fails in a large earthquake when the accumulated stress exceeds the frictional strength of the locked zone. The system has a recognizable cycle. You can monitor it. You can estimate how much strain has accumulated. You can build models that, while imperfect, give you some basis for probabilistic hazard assessment. The system has a kind of mechanical legibility. Walker Lane doesn't have that legibility. The strain is distributed across dozens of faults, many of which are not well mapped, many of which have insufficient historical records to constrain their recurrence intervals, and many of which interact with each other in ways that complicate simple stress accumulation models. The system can release strain in small increments across many faults, or it can concentrate strain on a subset of those faults and produce larger events. It can generate swarms that dissipate without a dominant rupture, or swarms that eventually organize into something more serious. From the outside, while you're in the middle of it, these different outcomes are very difficult to distinguish. Swarms in trans-tensional environments are known and have been studied. Walker Lane itself has produced comparable sequences in the instrumental record. The 2008 Mogul swarm near Reno, Nevada, close enough to be felt in the city, close enough to be felt in living rooms and to rattle dishes off shelves, produced hundreds of events over several weeks without a dominant main shock before eventually culminating in a magnitude 5.0 event that was significant enough to cause minor damage and a significant amount of anxiety. The sequence ran for a long time before it declared itself. The 2020 Monte Cristo range sequence in central Nevada showed similar behavior, prolonged swarm activity distributed over weeks without the clean decay pattern that follows a conventional main shock aftershock sequence. The catalogue entry for that sequence looks like the graph of a system that couldn't decide what it was, rather than the sharp spike followed by exponential decay that you'd see after a clean main shock. Walker Lane has done this before. The geological and instrumental environment is predisposed to this kind of behaviour. In that sense, the 218 event swarm is not anomalous for this specific region. It is, in fact, almost exactly what you would expect from a transtensional zone under elevated stress conditions. The anomaly is not the swarm itself. The anomaly, if there is one, is the timing. The fact that this swarm, entirely consistent with Walker Lane's established behavioural patterns, happened to be running during the same window that produced the Kermadec earthquake and the Mid-Atlantic Ridge cluster, on a planet already running a multi-week elevated seismic baseline. That's the coincidence being asked to carry a lot of weight in this story. But 218 events with no main shock, whatever their local tectonic logic, still demands a mechanistic explanation for their specific behaviour, and it's worth being clear about what the candidate explanations are and how confident we can actually be in any of them. The most straightforward and best supported explanation is distributed brittle failure in a transtensional stress environment. Picture the stress field in the Walker Lane region as a distributed load pressing on a population of faults, each with a slightly different orientation relative to the principal stress axis. In a simple stress environment with a single dominant fault orientation, most of the stress concentrates on the optimally oriented fault, and that fault fails when its threshold is exceeded. In a complex stress environment with a geometrically diverse fault population, no single fault is perfectly aligned with the stress field. The stress distributes across the population. Multiple faults approach their failure thresholds roughly simultaneously, rather than sequentially. You get activation across the population, many small events, each releasing a fraction of the total accumulated stress, rather than a single dominant rupture releasing it all at once. The analogy I find most useful for this is a crowd carrying a heavy object. If one person carries all the weight, that person either manages it or collapses under it in a single dramatic event. If 200 people each carry a small share of the weight, the crowd moves slowly and with a lot of shuffling and adjustment, but nobody collapses. The Walker Lane swarm in this model is the seismic equivalent of 200 people doing a lot of shuffling. Lots of activity, lots of small events, no single load-bearing failure. This explanation is mechanically sound and consistent with the observations. But it doesn't fully close the question, because consistent with and confirmed by are different things, and the second explanation introduces a complication that the first doesn't address. The slow slip versus brittle failure debate is the complication. In some extensional and transtensional environments, a significant fraction of the total deformation occurs not as discrete earthquakes, not as sudden brittle failure events, but as slow, continuous, seismic creep. Fault surfaces moving at rates too slow to generate detectable seismic waves. This process is invisible to standard seismic monitoring. The only ways to detect it are geodetic, GPS measurements, INSAR satellite data, tilt meters, which measure ground surface deformation rather than seismic wave generation. Slow slip is well documented in certain subduction zone environments, particularly in Cascadia and in Japan, where it plays a documented role in the seismic cycle of the overlying megathrust. Its role in continental strike slip and transtensional environments is less well characterized. The relevance for Walker Lane is this: swarms sometimes occur at the propagating boundary of a slow slip event. As the slow slip front moves through the subsurface, it perturbs the stress state of the surrounding locked fault zones, increasing stress on some sections, decreasing it on others, and the small earthquakes generated by those stress changes create the swarm signature at the surface. The swarm, in this model, is not the primary event. It's the acoustic shadow of a larger, slower, silent process occurring below the resolution of standard seismic monitoring. If this interpretation applies to Walker Lane, and to be clear, there is no direct evidence that it does in this specific case, then the swarm's behaviour would be expected to continue as long as the slow slip event is propagating, and the hazard assessment becomes considerably more complex. The question shifts from, will the swarm produce a main shock, to, what is the slow slip event doing to the stress budget of the broader Walker Lane system, and what does that mean for larger faults in the region over a longer timescale? The third candidate explanation sits at the more speculative end of the range, and it's the one that shows up most often in the less rigorous corners of earthquake discussion online, which is part of why it's worth addressing carefully rather than dismissing entirely: magma or fluid involvement. Some seismic swarms in extensional environments, and Walker Lane is extensional as well as strike slip, are associated with subsurface movement of fluids, either water migrating through fracture networks under pressure, or magmatic fluids associated with deep volcanic processes. The mechanism is well understood in volcanic settings. Fluid movement changes pore pressure along fault surfaces, effectively reducing the normal stress that keeps the fault locked, lowering the failure threshold, and generating swarms of small earthquakes as faults that were previously stable now slip under their reduced threshold. The application to Walker Lane is uncertain on multiple grounds. There is no surface volcanic activity in the affected area. The depth of the events, 1.5 to 8 kilometers, which is actually shallow even by Walker Lane standards, is consistent with upper crustal processes that could include fluid movement through shallow fracture networks. But the Basin and Range province, of which Walker Lane forms the western margin, does have geothermal activity in various locations, and the extensional tectonics of the region create the kind of permeable fracture networks through which hydrothermal fluids can migrate. The hypothesis is not absurd on physical grounds. It is, however, unsupported by the specific data from this swarm. Consistent with the physical environment and supported by the evidence are very different epistemic positions, and this explanation is solidly in the first category and not yet in the second. What the data does confirm, what is not speculative, not uncertain, not a matter of interpretation, is that this swarm is occurring in a region that is not seismically simple during a period of global seismic elevation, without the organizational structure that would allow seismologists to make confident short-term hazard statements to the people who live there. And that last point is the one that carries the most weight when you step back from the mechanics and remember what the numbers in the catalogue actually represent. Walker Lane is the only component of this 36-hour global cluster that has direct, immediate implications for populated areas. The Kermadec subduction zone is hundreds of kilometers from the nearest significant population centre. The Mid-Atlantic Ridge runs through open ocean. Nobody lives on the Mid-Atlantic Ridge. Nobody has to wake up in the morning and decide whether to keep their emergency kit by the door because of what the Atlantic Ridge seismometers are reading. Nevada has people, real ones. Reno, Carson City, Sparks, the communities that line the eastern front of the Sierra Nevada. These are places with addresses and schools and hospitals and unreinforced masonry buildings from the 1950s that were not designed with 218 event swarms in mind. For those people, the absence of a main shock is not reassuring in the way that it might superficially sound. Intuition says, no main shock means nothing big has happened, so things are probably fine. Seismology says, the absence of a main shock means we do not yet know what this sequence is or what it's going to do. Those are very different statements, and the gap between them is where the genuine uncertainty lives. The conventional wisdom about swarms, grounded in the catalogue of historical sequences, the statistics of how swarms evolve, the documented range of outcomes, is that a swarm without a main shock is one of three things. It is a swarm that is distributing its energy so broadly across so many faults that no dominant event will emerge, the crowd carrying the weight model, and it will eventually decay without producing anything large. Or it is a swarm that hasn't finished yet, still building, still loading the fault population, with the dominant event still ahead rather than behind. Or, and this is the one that nobody wants to be in, it is a foreshock sequence, a precursor to a larger event that the swarm is preparing the fault zone for, in ways that the real-time data cannot distinguish from the first two options. Seismology does not currently have a reliable method for distinguishing between these three scenarios in real time. There is research underway on machine learning approaches to swarm classification, on geodetic signatures that might distinguish aseismic slip from stress-driven brittle failure, on statistical features of swarm catalogues that correlate with eventual main shock production. Some of this research is promising. None of it has produced a tool that a seismologist could point to on April 17th and say, this specific swarm, in this specific location, is or is not going to produce a main shock in the next 72 hours. This is what seismology calls a forecasting failure mode. That phrase sounds harsh, and it's worth clarifying what it means. It does not mean that seismology has failed. It means that the physical system being studied has properties that make certain kinds of prediction fundamentally difficult, not because the models are wrong, but because the information needed to make the prediction is not accessible through any current observational method. The Gutenberg-Richter relationship, one of the foundational empirical laws of seismology, tells you what fraction of all seismic sequences of a given type eventually produce main shocks of various magnitudes. It's a population-level statistical description. It's accurate and well-validated at the population level. It tells you essentially nothing about whether this specific sequence in this specific location is going to be in the fraction that produces a main shock or the fraction that doesn't. The error bars on the probability estimate for any individual sequence are wide enough to encompass almost any outcome. So while the science is doing exactly what science is supposed to do, characterizing the uncertainty, quantifying what is and isn't known, providing population-level risk estimates, the people in Nevada are living in the gap between population-level statistics and individual event certainty. They're checking their phones, they're watching the USGS earthquake notification feed, they're counting the events, now 219, now 220, and wondering whether the number that matters is somewhere ahead of the current count or whether the current count is all there's going to be. This is the lived texture of what the seismic data represents, and it's worth sitting with that for a moment before moving back into the mechanics. Not just numbers in a database, not just catalogue entries. A population of people in an unresolved situation, waiting for a system to declare what it is, with no reliable way of knowing how long the declaration is going to take, or what form it's going to take when it arrives. The thread that ties Walker Lane back to everything we've been examining runs through the question of the global baseline. If the background rate of planetary seismic activity is genuinely elevated, not just in the 36-hour cluster window, but as a multi-week trend, then Walker Lane represents the most acute human consequence of that elevation. The Pacific component of this story is geographically remote from most people. The Atlantic component is literally in the middle of the ocean. Walker Lane is in the American West, in a region with population centers, in a system that is still actively evolving, producing new events, declining to resolve. It's the open process, the unresolved variable, the component of the global picture that is still writing its own conclusion in real time, in a place where that conclusion matters to specific people with specific vulnerabilities. The Pacific side of the story may be mechanically solved, stress redistribution from the March Tonga main shock, continuing through a predictable activation cycle. The Atlantic side may be coincidental clustering in a background system. Walker Lane is neither solved nor coincidental. It's still the question, suspended in the present tense, refusing to become past tense on anyone's schedule but its own. And here is where the historical record becomes relevant in a way that should focus the attention. Strike-slip systems in transtensional environments have produced some of the more unexpected magnitude escalations in recent seismic history, and the most instructive example is close enough in geography and geology to be worth examining carefully. The 2019 Ridgecrest earthquake sequence in the Mojave Desert of Southern California began on July 4th of that year with a magnitude 6.4 event. Large enough to be felt across Southern California, alarming enough to generate significant media coverage, but within the range of events that the San Andreas system and its adjacent structures produce on a recurring basis. Seismologists noted it, assessed the aftershock decay, and the scientific community moved into monitoring mode. 24 hours later, the sequence produced a magnitude 7.1, roughly 5 times more energy than the initial event, large enough to cause significant structural damage in the Ridgecrest area, large enough to generate ground failures, surface ruptures, and a regional felt area spanning most of the western United States. Nobody predicted it from the initial swarm behavior. The models didn't see it coming with any useful lead time. The sequence escalated on its own timeline, in its own way, without consulting the probability estimates. Ridgecrest is not Walker Lane. The geological specifics differ, the fault geometries differ, the distance from major population centres differs. But the general principle embedded in the Ridgecrest sequence applies to any swarm occurring in a complex transtensional stress environment. Swarms do not always stay swarms. Sometimes they organise. Sometimes that organisation happens faster than the models suggest it should, and on a different scale than the initial activity implied. The 2008 Mogul swarm near Reno produced hundreds of events, and then culminated in a magnitude 5.0. The 2019 Ridgecrest sequence produced a moderate event and then escalated to 7.1 within 24 hours. These two outcomes sit at opposite ends of the range of possibilities for any given ongoing swarm, and real-time seismology cannot reliably tell you, while you're in the sequence, which end of that range you're heading toward. Statistically, most swarms stay swarms. The probability that any given swarm will produce a main shock significantly larger than the largest event so far in the sequence is, by historical base rates, not the most likely outcome. The mathematics favours the scenario where Walker Lane dissipates, where the 218 events represent the bulk of the energy release, where the sequence gradually slows and the catalogue entries thin out, and the story ends not with a dramatic escalation, but with a quiet trailing off that doesn't generate any headlines. That is the statistically most likely outcome. But statistically most likely and guaranteed are separated by exactly the width of the uncertainty range, and in a region with population centres, with buildings of variable construction quality, with people who have been watching their notification feeds for days, that uncertainty range is not an abstraction. It's the difference between a week that becomes a footnote and a week that becomes a before and after marker in the lives of people who happen to live in western Nevada. The Walker Lane swarm is still the most alive part of this story. The Kermadec magnitude 6.0 is geology. The Atlantic Ridge Cluster is geology. Walker Lane is geology and hazard and uncertainty, and human consequence all running simultaneously in the same dataset, which is what happens when the Earth's mechanical processes intersect with the specific locations where human civilization has chosen to put down roots. And that intersection between the planet's mechanical logic and the human geography that is spread across it is ultimately what makes any discussion of seismic patterns more than an academic exercise. The Earth doesn't know Reno is there. The faults don't route themselves around population centres. The stress redistribution processes that drive swarm behaviour in transtensional zones operate entirely independently of the fact that people have built cities in the region where those processes express themselves. Walker Lane was still adding events to its count when the other two components of the global cluster had already become history. It was still uncertain when the Pacific and Atlantic had become resolved, or at least resolvable. It was the open edge of the 36-hour story, and it remained open long after the window that defined the story had formally closed. And that open edge is the bridge to the larger question, the question that this entire cluster has been circling since the first data points appeared on the global map. Not what happened in these three systems. We've walked through that. Not are these three systems mechanically connected. We've examined that and found the connections wanting. The question is what the baseline underneath all three of them is doing, and whether the elevated background that made this cluster visible is a transient fluctuation or a directional shift. Walker Lane, still generating events, still refusing resolution, still relevant to people with addresses in the real world, Walker Lane is the most human face of that larger question, which is why we're not done with it yet, even as we move toward the broader picture that contains it. Part 5. Global background radiation. There is another layer that needs to be added at this point, because stopping at averages and global distribution still leaves something unresolved in how this particular window behaves when placed against longer seismic history. Even if we accept that 78 magnitude 4.5 and greater earthquakes in 7 days is statistically normal, and even if we accept that multiple regional clusters can overlap by chance, there remains a qualitative difference between random distribution and clustered simultaneity across multiple tectonic regimes. That distinction is subtle, but it matters, because Earth does not just produce earthquakes as isolated points in time. It produces sequences, cascades, and diffuse fields of stress release that sometimes appear locally organized and sometimes appear globally fragmented. Most of the time, those behaviors are separated clearly enough that interpretation is straightforward. A large earthquake occurs, aftershocks follow, and the system gradually relaxes. Or a swarm develops in a localized zone without a clear main shock, and the interpretation remains regional. But occasionally, multiple systems enter active states at once, without any single dominant initiating event that clearly connects them. And when that happens, interpretation becomes less about individual causality and more about system-wide state. This is where the idea of a global seismic state becomes analytically useful, even though it is not formally defined in standard seismology. It is not a claim that Earth has phases in a deterministic sense, like a heartbeat or a cycle with fixed intervals. Instead, it is a way of describing how the probability field of earthquake occurrence changes over time across the entire planet. In simpler terms, the Earth is always producing earthquakes, but the shape of where and when those earthquakes are likely to occur is not constant. It fluctuates based on stress accumulation, redistribution, and release patterns across interconnected but not directly synchronized tectonic systems. And during the window we are examining, that probability field appears to have been slightly compressed in time. Not dramatically, not in a way that violates expected ranges, but enough that independent systems became more likely to produce events that overlap within the same narrow temporal window. That is the first important refinement beyond simple averages. But there is a second refinement that is often overlooked in public interpretations of global seismicity, and it relates to how earthquake catalogues themselves encode uncertainty. Every global earthquake catalogue is a reconstruction of reality based on sensor networks, detection thresholds, and location algorithms. That means every event carries with it not only a magnitude and a time, but also an implicit margin of error in both parameters. Small shifts in reported origin time or depth can change how events appear in relation to one another when viewed at global scale. This matters because when we talk about simultaneity across multiple systems, we're often compressing uncertainty into apparent precision. A few seconds or minutes of difference in origin time can be invisible in narrative framing, but significant in statistical modelling. Similarly, depth values, especially the repeated use of default or constrained solutions such as 10 kilometers, can create artificial visual alignment between otherwise unrelated events. This is not a flaw in the system. It is a limitation of how global seismic monitoring necessarily works. But it does mean that apparent synchronization can sometimes be amplified by how data is standardized for reporting. Once this is understood, a large portion of the perceived pattern begins to soften. The sharp edges of simultaneity become slightly blurred, but not completely erased, because even after accounting for catalogue artifacts, spatial clustering remains. And spatial clustering is more difficult to dismiss. During this window, we are not simply seeing a high number of earthquakes. We are seeing elevated activity distributed across multiple major tectonic boundaries that are not typically active in lockstep. The Kermadec subduction zone represents one of the fastest converging plate boundaries on Earth. It is a region where the Pacific plate is being forced beneath the Australian plate at a rate that can exceed several centimetres per year. This is a high-energy system capable of producing very large earthquakes, including events well above magnitude 8. It is also a system that has shown sustained activity in the weeks leading up to the window being analysed, including the broader Tonga-Kermadec sequence that has been under observation. The mid-Atlantic ridge, by contrast, is a divergent boundary. Here, tectonic plates are moving apart, and new crust is being created as magma rises to fill the gap. Earthquakes in this environment are typically smaller, shallower, and more related to transform fault adjustments along segmented ridge offsets than to large-scale compressional failure. The Walker Lane Belt introduces an entirely different mechanical regime. It is a continental shear zone, a region where the North American plate is internally deforming to accommodate motion between major plate boundaries. It is not a clean fault line, but a distributed zone of deformation, where strain is spread across multiple faults and fractures rather than concentrated along a single rupture plane. These three systems are mechanically unrelated in the sense that they do not directly transfer stress to one another in a short-term causal chain. There is no known physical model in which a rupture in the Kermadec Trench directly triggers a swarm in Nevada or a cluster along the mid-Atlantic ridge within hours or days, and yet they are all active within a narrow temporal window. This is where interpretation begins to split into competing frameworks. One framework treats this as pure coincidence, amplified by high background activity. In this view, Earth is always producing earthquakes across multiple systems, and occasionally those independent processes overlap in time. The more active the background, the more likely these overlaps become. There is no deeper connection required, and no hidden coupling mechanism is necessary to explain the observation. Another framework allows for a weaker form of interaction, not direct triggering across systems, but indirect modulation of stress sensitivity following major seismic events. In this view, large earthquakes such as those earlier in the broader sequence, particularly in the Tonga and Indonesian regions, could slightly alter stress conditions globally through dynamic wave propagation. These waves travel around the planet and can, in some cases, trigger small adjustments in already critically stressed faults. However, even in this model, the effect is short-lived and localized. It does not naturally extend into a coherent explanation for multi-system clustering across different tectonic regimes over a 36-hour window without additional assumptions. A third, more speculative framework suggests that Earth's lithosphere may behave as a more interconnected stress system than currently modelled, where large-scale redistribution of stress can subtly modulate failure probabilities across distant faults. This idea appears in fringe geophysical discussions, often tied to mantle dynamics or deep structural coupling, but it remains poorly constrained and lacks predictive capability. The key issue across all of these frameworks is not whether they are mathematically possible, but whether they are necessary. Because the simplest explanation, statistical clustering inside a high-activity baseline, already accounts for most of the observed behaviour without requiring additional mechanisms. But simplicity does not always resolve perception, and perception is where this phenomenon becomes most interesting. Because when multiple independent systems become active simultaneously, the human brain does something very predictable. It compresses spatially distributed events into a single coherent narrative. This is not a mistake in cognition, it is a survival feature. Humans are pattern detection systems optimized for environments where correlations often imply causation. In natural environments, detecting a pattern quickly can be the difference between safety and danger. But Earth's tectonic system is not a human-scale environment. It operates on frequencies, timescales, and spatial distributions that exceed intuitive interpretation. So when independent seismic systems align temporally, the brain does what it is designed to do. It seeks structure. This is why the phrase opposite sides of the planet carries more psychological weight than it does scientific meaning. It creates a visual symmetry that reinforces the impression of linkage. A subduction zone on one side of the globe and a ridge system on the other appear conceptually balanced, even though there is no mechanical relationship between them. This symmetry is cognitive, not geophysical. But it still shapes interpretation. At this point in the analysis, after removing direct mechanical linkage, removing solar forcing as a valid trigger for this specific window, and accounting for catalogue and distribution effects, what remains is a system that is behaving within expected statistical bounds, but doing so in a way that produces unusually coherent temporal overlap. And that is where the discomfort begins. Because statistical normality does not always feel normal when it organizes itself into patterns that resemble structure. This is especially true when multiple independent systems, subduction zones, mid-ocean ridges, and continental deformation belts are active at the same time. Even if each system is behaving within its own expected range, their simultaneous activity creates a composite signal that feels more organized than it actually is. This is the core tension at the center of this entire discussion. The Earth is not necessarily becoming more active in a fundamental sense. There is no clear evidence in this window of a global increase in seismic energy release beyond normal variability. But it is also not perfectly stable in its distribution of activity, and when variability aligns across multiple systems, even briefly, it produces the impression of coordination. This leads to the final interpretive challenge. If the observed clustering is purely statistical, then similar windows should exist throughout seismic history, and indeed they do. Retrospective analyses of global catalogues reveal many periods where multiple regions show overlapping activity within short timeframes. What makes the current window feel different is not its absolute magnitude, but its narrative clarity. The combination of regions involved, Kermadec, Mid-Atlantic Ridge, Walker Lane, creates a geographically balanced structure that is easy to visualize as a global system. This is a form of selection bias, not in the data itself, but in how the data becomes meaningful when arranged in certain spatial configurations. So the final conclusion, if we strip away narrative framing, is that there is no evidence of a new global seismic mechanism operating in this window. There is no confirmed interconnection between the systems involved. There is no solar or atmospheric driver that aligns with the timing of events, and there is no indication of a structural shift in Earth's tectonic behavior beyond normal variability. But there is something else that is equally important, even if it is less dramatic. There is an elevated background state of activity across multiple regions that increases the probability of temporal overlap, and when that overlap occurs across systems that are geographically and mechanically distinct, it produces a pattern that is visually striking even when it is statistically expected. That is the core paradox. Nothing unusual is happening in any single system. But multiple normal systems behaving normally can still produce something that looks extraordinary when viewed at the right resolution. And that is why this story persists. Not because Earth has changed its behavior in a fundamental way, but because the conditions for noticing alignment between independent processes have temporarily increased. In the end, what we are observing is not a hidden global mechanism, but a convergence of independent activity inside a system that is always active, always variable, and always capable of producing moments that look meaningful, even when they are not connected. And the real challenge is not explaining the earthquakes, it is learning how to interpret a planet where meaningful-looking patterns can emerge without any underlying coordination at all. That is where the science ends, and the interpretation problem begins. Part 6. The psychology of the pattern. Let's talk about what your brain did the moment you read the title of this story. It made a map, it plotted 3 points, it connected them, and then something in the machinery of your perception said, "That's not random, that's a shape. That shape means something." You probably didn't experience this as a deliberate analytical step. It happened before analysis, before evaluation, before the rational part of your mind had a chance to weigh in. The pattern was recognized before you decided to recognize it. This isn't a flaw in your cognition. It's one of the most sophisticated features of the human perceptual system, the product of hundreds of thousands of years of evolutionary pressure toward fast pattern recognition in noisy environments. The organism that sees a tiger-shaped shadow in the grass and runs is more likely to survive than the organism that demands a thorough statistical analysis before reacting. The cost of a false positive, running from a shadow that turns out to be a log, is low. The cost of a false negative, standing still for the actual tiger, is not. Evolution optimized heavily for sensitivity to patterns at the expense of specificity. We see patterns everywhere, including in random noise, including in earthquake catalogues. And here is something worth sitting with before we go any further. You didn't choose that response. It wasn't a decision. The pattern recognition happened to you, the way a reflex happens to you, before the deliberate part of your mind was even invited into the room. The machinery that generated it is ancient. It predates language. It predates reasoning. It predates the concept of a tectonic plate by several 100,000 years. That machinery is extraordinarily good at the job it evolved to do. The problem is that the job it evolved to do was not evaluate global seismic catalogues for statistically meaningful clustering. It was survive. And those two jobs require very different calibrations. The global map amplifies this tendency considerably. There's something about the visual format of a globe with seismic events plotted on it that makes the pattern completion instinct go into overdrive. The Earth is a sphere. Spheres are geometrically regular. When you see 3 points distributed across a sphere at roughly equidistant positions, your brain doesn't just notice them, it interprets them as vertices of a structure. The triangle isn't in the data, the triangle is in the visual presentation of the data. And once the triangle is in your visual cortex, it's extremely difficult to dislodge through rational argument alone, because the rational argument is happening in a different part of the brain from the pattern recognition, and the pattern recognition doesn't take notes. Think about what that means practically. You can explain to someone carefully and accurately that the 3 events in question span 3 mechanically unrelated tectonic systems, that no validated mechanism connects them across those distances, that the probability of temporal overlap at these activity rates is not small. You can walk through all of it, and they will nod, and they will follow the logic, and somewhere in the background the triangle will still be there, intact, because the argument and the image are not competing for space in the same cognitive room. The image got there first, it furnished the room. The argument is trying to redecorate. This is not a problem specific to people who are scientifically unsophisticated. It is a problem for everyone, including scientists, including seismologists, including the people who build the catalogues. The visual representation of data is never neutral. The choice is made about how to present seismic data on a global map, which events to include, what size to render the dots, what colour scale to use for depth or magnitude. All of those choices shape what the human visual system will do with the information before the analytical mind gets a single vote. A seismologist looking at a well-designed global activity map is having the same initial perceptual response as anyone else. The difference is in what happens in the second step, after the pattern is recognised. The trained analyst has tools to interrogate the pattern that the untrained observer may not. But the first step, the automatic recognition, the triangle appearing in the visual cortex, that part is the same for both. Temporal clustering has the same property. When events happen close together in time, the human mind assumes causality. It's the post hoc ergo propter hoc fallacy at scale. After this, therefore because of this, the Kermadec earthquake happened, then the Atlantic Ridge cluster happened, then the Walker Lane swarm was already happening. The sequential exposure creates an impression of narrative, a story with a beginning, a middle, a development, a consequence. But earthquake catalogues are not narratives, they're measurements. The time axis is real, but the connections between points on that axis are not automatically real just because the mind wants to draw them. The narrative pull is especially strong in this case because the events are genuinely interesting individually. Kermadec is a real subduction system with real history and real ongoing hazard. The Mid-Atlantic Ridge is a real divergent boundary producing real clustering behaviour that is at minimum worth documenting even if the significance is unclear. Walker Lane is a real transtensional zone with real implications for real people in real populated regions. None of these things are invented. None of them are being artificially amplified by selection or framing. They are what they are. The problem is that interesting individually and meaningfully connected are different claims, and the narrative format, which requires stories to have causally linked events, will tend to collapse the distance between them in ways that data analysis would not. Media framing reinforces this structural illusion in ways that are worth making explicit. Earthquake coverage tends to emphasize geographic extremity, opposite sides of the planet, because extremity is a legitimate marker of newsworthiness. When 3 events occur and 2 of them happen to be geographically distant, the coverage will almost always frame that distance as significant. The framing then shapes how subsequent audiences interpret the data. By the time a viewer has read 3 separate articles or watched 2 videos about a seismic cluster, the global synchronization framing has already become the lens through which they're processing new information. Correcting that framing after the fact is much harder than preventing it, because the correction requires dismantling a cognitive structure that the visual and temporal presentation of the data actively reinforced. There's a specific vocabulary that amplifies this effect, and it's worth naming because it shows up consistently in coverage of exactly these kinds of global seismic clusters. Words like simultaneously, words like synchronized, words like linked These terms carry causal implication embedded in their ordinary language meaning. To say two things are synchronized is to say they are operating in coordination, which implies a connecting mechanism, which implies that one has something to do with the other. To say events are linked is to assert a connection as a factual matter rather than raise it as an investigative question. The vocabulary of connection precedes any evidence of connection, and once it's in circulation, it shapes what questions people think need answering. Instead of asking, "Are these connected?" the reader is already asking, "How are these connected?" which is a fundamentally different inquiry, with a fundamentally different default assumption embedded in it. The earthquake data is inherently high frequency in the statistical sense. There are a lot of events, they're continuously generated, and the catalogue is always full of potential pattern elements waiting to be connected. This makes the earthquake domain particularly susceptible to apophenia, which is the technical term for the perception of meaningful patterns in random or meaningless data. Stock market charts, constellations in the night sky, faces in clouds. Humans are extraordinarily good at finding meaning in noise, and the earthquake catalogue is a very noisy dataset with a very large number of potential pattern elements. And there is something specific about the earthquake catalogue that makes apophenia especially likely. The events are real. When you see a face in a cloud, some part of you knows it's a cloud. The face is an illusion and the cloud is the reality. When you see a pattern in an earthquake catalogue, the earthquakes are not illusions. They are real events, real ruptures, real energy releases, real entries in real databases maintained by real scientific institutions. The pattern you're perceiving is being drawn from genuinely existing data points. This makes it considerably harder to dismiss the pattern as pure projection, because you're not projecting onto nothing, you're projecting onto something. And the fact that something real is there makes it much easier to convince yourself that the connection you're seeing is also real, even when the connection is the projection and the earthquakes are the cloud. None of this means the pattern you observed is meaningless. That's the critical distinction. Acknowledging that human pattern recognition is fallible is not the same as saying that all patterns are false. Some patterns in earthquake catalogues are real. Some elevated activity periods represent genuine changes in the background state. Some global clusters are worth scientific attention precisely because they don't resolve into simple coincidence explanations. The discipline is in distinguishing between the two, and the tool for making that distinction is statistics applied carefully, not pattern recognition applied quickly. So where does that statistical discipline leave us with this specific cluster? With three competing interpretations, none of which fully resolves the data. The first interpretation is statistical clustering. The global seismic rate was elevated. Elevated rates produce more clustering. The 36-hour window contained a cluster. The cluster was perceived as a pattern. The pattern is a cognitive artifact, not a physical signal. This explanation is the most parsimonious. It requires the fewest additional assumptions, and it's consistent with everything in the data. Its weakness is that it doesn't specifically explain why this cluster occurred during an already elevated background period, and it doesn't tell us what's driving the background elevation. The statistical explanation can absorb the cluster into the expected range of behavior, but the background elevation that produced the elevated clustering rate is itself a fact that the statistical explanation doesn't account for. It explains the figure, but not the ground. The second interpretation is delayed global stress redistribution. The March magnitude 7.5 in Tonga sent stress waves around the planet. Some of those waves perturbed fault systems already near their failure thresholds. Weeks later, some of those perturbations resulted in triggered events in the Atlantic and Nevada. The connection is real, but attenuated beyond statistical attribution. This explanation is partially plausible. The mechanism is real. The scale of connection is uncertain. Dynamic triggering is documented. It has happened at ranges of thousands of kilometers. The 2002 Denali earthquake triggered seismicity at Yellowstone. The 1992 Landers earthquake lit up much of the western United States. These are facts. The problem isn't the mechanism. The problem is the window. Most researchers accept dynamic triggering on timescales of hours to a few days following the initiating event. Extending that window to weeks, which is what would be required to connect March's Tonga main shock to April's Atlantic and Nevada activity, is beyond what the current literature supports with confidence. And when you extend the window, you also extend the number of candidate random coincidences, which weakens the statistical case for a causal connection, even as it makes the mechanism more theoretically flexible. The third interpretation is what you might call the emergent lithospheric excitation model, the idea that the global lithosphere sometimes enters periods of elevated sensitivity, where multiple fault systems become simultaneously more responsive to perturbation, not because of a single triggering event, but because of some diffuse, large-scale change in the stress environment. This is speculative fringe territory. There's no validated mechanism for it. It doesn't fit neatly into current plate tectonics theory. And yet it has a certain mechanical intuition behind it, the idea that a planet-sized elastic shell might have system-level modes of behaviour that we haven't yet identified because our observation period is too short and our instrumentation too sparse. The Earth has been doing this for 4.5 billion years. We've had global seismic networks for about 60. The ratio of observation window to system lifetime is not favourable for confident claims about what modes of behaviour are and aren't possible. This explanation is interesting precisely because it's unfalsifiable with current data, which is simultaneously the reason to be cautious about it and the reason to hold it as a genuine open question. None of these three explanations fully resolves the observation. The statistical clustering story doesn't explain the background elevation. The stress redistribution story doesn't survive the attribution problem at global scales. The systemic excitation story has no mechanism. This is what scientific humility looks like at the boundary of current knowledge, not we don't know anything, but we know enough to know that our models are incomplete. Those are very different admissions. The first is paralysis, the second is orientation. The data is insufficient for global claims. That sentence needs to be said clearly, and it needs to be heard clearly, because in an information environment that rewards confident explanations over honest uncertainty, the honest answer is almost always underpowered relative to the confident one. Confident wrong is louder than uncertain right. It always has been. The honest answer in this case is, something happened during this 36-hour window that was worth noticing. We know what each component of it was locally. We cannot confirm that the components are physically connected. We cannot confirm that they're purely coincidental. The background elevation is real and unexplained. The pattern is visually compelling and mechanically ambiguous. Sitting with that ambiguity without resolving it prematurely in either direction is harder than it sounds, because the mind wants resolution. The mind finds unresolved patterns genuinely uncomfortable. There is a well-documented psychological phenomenon called the need for cognitive closure, the drive to reach a definitive answer and end the uncertainty, and it applies as much to scientific questions as to any other kind. The pressure to close the loop to say either this is definitely connected or this is definitely coincidence is real. Resisting it is a skill. It's one of the core skills of empirical reasoning, and it's exactly what this data demands. And yet Walker Lane is still active. The Ring of Fire is still running above its recent baseline. No system has fully stabilized. The planet hasn't gone quiet. Which means the question we started with, whether this represents meaningful global stress behavior or a high visibility coincidence inside a naturally noisy Earth, is still open. And maybe that's the most honest thing to say about it. The question is still open, and the data that would close it either doesn't exist yet or would require a level of global seismic monitoring that we don't currently have. The mid-ocean ridge systems are instrumented at a fraction of the density of continental fault systems. The deep ocean floor, where a significant portion of the Earth's tectonic boundary activity occurs, is essentially a blind spot in the global catalogue. We don't know what we're not seeing. And we don't know what we're not seeing is a very different epistemic position from the pattern we're seeing is the pattern that exists. Here's what we do know. The three systems that appeared in this window represent three fundamentally different tectonic processes. Compression at Kermadec, extension at the mid-Atlantic ridge, shear at Walker Lane. If the planet were truly operating as a single interconnected mechanical system in some elevated state, you would expect to see precisely this kind of multi-regime activation, because a global stress elevation wouldn't target just one boundary type. It would be visible across boundary types, because all boundary types are part of the same continuous lithospheric shell. The observation is consistent with the hypothesis. It doesn't prove the hypothesis. Consistency with a hypothesis is not the same as evidence for it. But it's not nothing either. The philosopher of science Karl Popper spent a career explaining why consistency with a theory is a much weaker form of support than most people intuitively assume. Any sufficiently flexible theory can be made consistent with almost any observation. The question isn't, is this consistent with the idea of global lithospheric excitation? The question is, what observation would be inconsistent with it, and have we looked for that observation? We haven't, not rigorously, not with the monitoring infrastructure that would be required to do it properly. So the hypothesis remains in the category of interesting speculation that hasn't been seriously tested, which is a different category from both confirmed and refuted. The Earth is a 4.5 billion-year-old machine of almost incomprehensible complexity, operating over timescales ranging from microseconds to eons, with internal dynamics that we can measure only at its surface through instruments that have existed for roughly 100 years. The idea that our current models fully capture its behaviour is, historically speaking, a claim that has been wrong before. Plate tectonics itself was considered fringe science within living memory. The mechanisms of deep focus earthquakes weren't understood until well into the 20th century. The existence of slow earthquakes, seismic slip events that release energy over days to weeks without generating conventional seismic waves, was only definitively confirmed in the last few decades. Every generation of seismology has been surprised by the behaviour of a system that turns out to be more complex than the previous generation's models allowed for. That's not a reason to embrace every speculative claim about global seismic synchronization. It's a reason to hold the boundary between "we don't know" and "this can't be" with some care. Those two statements are not the same. "We don't know" is an honest epistemic position. "This can't be" is a theoretical commitment that the history of Earth science does not entirely support. The frontier of our uncertainty is real. The behaviours at that frontier are worth watching, and worth watching without having already decided what they mean. Walker Lane is still generating events. The Tonga-Kermadec system hasn't returned to pre-March baseline behaviour. The Mid-Atlantic Ridge cluster sits in the catalogue, temporally compressed, mechanically unexplained, and somewhere in the background, at a rate that may or may not be meaningfully above the long-term average, the planet continues producing the 70 to 80 events per week that constitute its normal operating noise. The final question, the one that probably won't stop running in the background of your thinking after this is over, is this. Are we watching noise become visible? Better instruments, better catalogues, better global coverage, more data flowing through more algorithms, finding more apparent patterns in what was always a noisy system? Is the perception of elevated global activity an artifact of improved observational capacity, making the normal look abnormal? 20 years ago, the Walker Lane swarm might have appeared in regional catalogues without making it into global summaries. 20 years ago, 3 magnitude 5 events on the Mid-Atlantic Ridge within 16 hours might have been logged without ever being placed in the same sentence as activity in Nevada and the Southwest Pacific. The integration of global seismic data into unified, publicly accessible, visually navigable platforms is a recent development. It changes what patterns become visible to people, including scientists. And visibility is not the same thing as significance, even when what's being made visible is real. Or is something actually different, the background rate genuinely shifting, for reasons we haven't identified, in a direction that the next decade of seismic data will either confirm or refute? The geological record contains periods of elevated global seismic activity that stand out even against the deep time baseline. Not all elevated periods are equal. Some are transient fluctuations that regress to the mean within months. Some mark the beginning of longer-term adjustments in the stress state of regional systems. We are not yet at a temporal distance from this window that would allow us to say which category it belongs to. We are inside it. We are watching it in real time. And watching something in real time while you are inside the event is one of the worst possible vantage points for evaluating its significance, because significance is often a property of duration that only becomes visible in retrospect. The honest answer is that we cannot yet tell. Both possibilities are live. The instrumentation argument is real. Seismic monitoring has improved substantially over the past 2 decades, and more comprehensive global coverage does make clustering more visible in ways that could be misread as anomaly. A quiet decade in the 1980s might look very different from a quiet decade now, simply because the catalogue in the 1980s wasn't capturing everything it should have been. The apparent increase in detectable seismic events globally over the past generation is at least partly an artifact of improved detection thresholds, not purely a reflection of increased seismic activity. Distinguishing those two contributions, the observational and the real, requires analytical tools that operate on catalogue completeness and network sensitivity that most public discussions of seismicity don't even attempt. But the background rate data is also real, and the multi-week elevation across multiple Ring of Fire segments is in the catalogue regardless of how we interpret it. What we're left with, at the end of this 36-hour window and everything it contained, is a planet that is doing what planets do, redistributing stress across a fragmented shell, occasionally generating observable clusters that look more organised than they probably are, occasionally producing surprises that remind us the models are approximations and not truths. The Earth doesn't care whether our models explain it. It doesn't organise its behaviour around our categories. It just continues, compressing here, extending there, shearing along the boundaries between, on its own timetable, in its own language, with a vocabulary we're still learning to read. We have 70 to 80 magnitude 4.5 events per week as our baseline, and we have a week that produced 78, and we have a 36-hour window within that week where 3 mechanically distinct systems produced visible events simultaneously, and we have a background context of elevated multi-system activity, and we have Walker Lane still adding to its count, and we have the knowledge that our models are adequate for the local and insufficient for the global. That's where the data leaves us, not with answers. With a better framed question, is this just noise becoming visible for the first time? The natural consequence of watching an ancient, complex system with sharper eyes than we've ever had before? Or is the planet entering a more interconnected stress state that our current models don't have the architecture to describe? Those are not equivalent questions with equivalent evidence pointing toward them. The first is simpler, better supported, consistent with everything we know about how observational improvements change apparent signal in noisy data sets. The second is more dramatic, less supported, and makes claims that go beyond what the data can currently validate. If this were a bet, the smart money is on the first. But the smart money has been wrong before about what the Earth was doing, and the smart money didn't have slow earthquakes in its models until slow earthquakes showed up anyway and had to be accounted for. The seismometers are running, the catalogues are growing. The next event will be logged somewhere, in some system, at some depth, with some catalogue assigned number. And the question of whether it's signal or noise, whether it's part of a pattern or just another count on the tally, will still be waiting for an answer that the data hasn't given us yet. The Earth is patient in ways that we are not. It has been doing this for 4.5 billion years before we built a single seismometer. It will be doing this for billions more after the last one goes offline. We are, in the most literal sense, very new observers of a very old system. Trying to find meaning in the record of a process that operates on timescales our species hasn't existed long enough to fully witness. The entire period of human civilization, every city, every written language, every war, every dynasty, every empire, the whole span of recorded human history is less than the blink of an eye against the timescale on which the tectonic system operates. We have been watching for a geological instant. We have built models from a geological instant of data. And we are now trying to determine, from inside that instant, whether the behaviour we're seeing this week is normal or anomalous, against a baseline that would require millions of years of continuous observation to fully characterise. That is an extraordinary thing to attempt. The fact that seismology gets as far as it does, that it produces working hazard maps and useful probability estimates and life-saving early warning systems, is genuinely remarkable given the constraints. But those achievements exist alongside real limits, and the limits matter here, because this specific question, whether the 36-hour window represents something more than coincidence, sits exactly at the edge of where the achievements stop and the limits begin. The 36-hour window is closed. The question it opened is not.